This is the second part of the blood pressure instrumentation. Prior to start with this part, we make a small recap of the first part, which is a general background. In the general background, we started with a small introduction about the blood pressure instrumentation. We talked about what is a blood pressure, about the unit of measurement of the blood pressure, about the different classification schemes, and we have selected the measurement method as a classification scheme where we can measure either invasively or non-invasively, and we use this in this lecture. And we have make a small comparison between the invasive and non-invasive blood pressure readings. Then we move to talk about commercial applications of blood pressure readings in vital signs and patient monitors. Also, we talk about the non-invasive blood pressure module, and it's made up of a rolling pump, two pressure sensors, and two solenoid valves. Then we talked about the non-invasive blood pressure accessories such as the connectors and non-invasive blood pressure cuffs. Then we move to talk about the cardiovascular system and the regulation of the blood pressure in the cardiovascular system. We said that the cardiovascular system is made up of two circuits, a low pressure circuit, which is pulmonary circuit, and a high pressure circuit, which is systemic. We have talked then about the importance of control the pressure, regulating the pressure in the cardiovascular system. Also, we have talked about the structures and the structure and the dimensions of the different blood vessels, the large, the medium, and the small ones, as well as the capillaries. We start to talk about the blood pressure regulation using the mean arterial pressure and the formula which is used in this, which is the mean arterial pressure equals the multiplication of the cardiac output and the total peripheral resistance. And the cardiac output, as we know, it's equal to the heart rate multiplied by the volume stroke. Then we have talked about the regulation of the mean arterial pressure and its importance. We related this to the perfusion. We said in order to have a good perfusion, we need a good control of the mean arterial pressure. The perfusion is very important in order to have a healthy tissue, because it's responsible for the supply of these tissues with oxygen and nutrients, and the removal of CO2 and metabolic waste. Then we talked about the mechanism of mean arterial pressure regulation. We have a short term and a long term. The short term, it extends from a few seconds to a few minutes, whereas the long term extends from hours up to days. Then we talked about that the short term can be also separated into a rapid and intermediate one. And the rapid is mainly controlled by a neural mechanism, which means by neurons, a special type of neurons, which is the baroreceptors and chemoreceptors. As for the intermediate, short-term intermediate response is controlled by hormonal, and finally the long-term is controlled by the body fluid control activity. We said in summary that we use a different type of sensors in order to make the control of this of the mean arterial blood pressure. We use strain gauges which is the baroreceptors, a special type of neurons, measuring the variation in the diameter in a high pressure circuit, which is systematic, and also in the low pressure circuit, which is pulmonary. Also, we used chemical sensors, which is pH, CO2 and O2, which is in the which is a special type also of neurons. Also, we said in the long term we use sodium. We need to make the conservation of sodium and water, so we need also a sodium sensor. So in the control of the mean arterial pressure sensor, our body use a biological sensors, which measure a biological strain gauges, biological pH, CO2, O2, and A plus sensors. A biological one using in the control loop of the blood pressure regulation. Now we will start with the invasive blood pressure instrumentation. In the invasive blood pressure instrumentation, we will have an introduction and the talk about the two major types of the invasive blood pressure instrumentation, extravascular and intravascular, which means that the sensor will be inside the blood vessel in the intravascular and outside the blood vessel in the extravascular, which also means that we have an interface between the blood pressure signal which inside the blood vessel and the sensor, and we will make a modeling for this one. Another name for the extravascular is a side stream, and another name for the intravascular is mainstream. We will start now with an introduction about the invasive blood pressure. In the study of the invasive blood pressure, three prerequisites are needed: a knowledge of the signal processing, a knowledge of modeling, and a knowledge of electronics. And we will use these backgrounds in the design of invasive blood pressure. So the first attempt made to measure the blood pressure was made on a horse in 1773. In this diagram, we see the blood pressure readings in different places or sites in the cardiovascular system. In this slide, we see the different access sites in order to measure the blood pressure invasively. We use catheters with different sizes. As we can see, they have different lengths and different diameters with different colors. The blood pressures and the blood samples can be taken through the use of this catheter. Now we will start to talk about the ideal arterial pressure waveform. As we said before, we need signal processing background in order to understand the design of the invasive blood pressure instrument. So inside the inside the aorta, we have this reading after the aortic valve. We have this reading for the blood pressure, arterial blood pressure. The first point we should stress that this wave is a periodic wave. And we will study later what means a periodic wave. Also, another point concerning this wave, we need to have three readings from this wave. We need to calculate the systolic pressure, which is the maximum pressure during the contraction of the heart. We need to calculate the diastolic pressure, which is the minimum blood pressure during the relaxation of the heart. And finally, we need to calculate the mean arterial pressure, which is used in the control of the blood pressure regulation of the cardiovascular system, as we said before. We have two ways to calculate the mean, either an approximated calculation or an accurate calculation. An accurate calculation, we need to make the integration of the area below the waveform in one period. So, as we said, the first point, this wave is a periodic wave, and we need to make three readings, which is the systolic, mean, and diastolic. So we will start now with the talk about the extravascular type of the invasive blood pressure measurement. The extravasculars means the pressure, as we said before, outside the blood vessel, which means that we should have an interface or a connection between the pressure inside the blood vessel and the pressure sensor. The arterial blood pressure wave is transmitted by a catheter, which we need to make a model for this one to study the impact of this on the transmission of the signal or of the arterial blood pressure wave. Then measure this after the receiving of the pressure or the blood pressure wave by a catheter. We measure it by a pressure sensor. The pressure sensor will be a Whitson bridge, which is made of 4 strain gauges. The catheter is modeled as an RLC circuit, and we will see that later. The pressure sensor or the invasive blood pressure, the extravascular invasive blood pressure, is considered according to the IEC, International Electrotechnical Commission, as an applied part CF, which means cardiac floating. This is the set which is used in the measurement of the extravascular invasive blood pressure. As we said before, we have a catheter which is inserted inside the blood vessel. Then this is connected to this part here. This is the line which we need to make modeling for it, which is transmitted the blood pressure wave to this catheter. However, we shouldn't have a blood in this part, because if the blood will be here, it's possible to have a clot, and this will prevent the transmission or the measurement of the pressure waveform. For this, we use saline, hyperonized saline, which is a bag which is put here with under certain pressure and the specific slow flow. So the hyperonized saline will be transmitted through this line, through the pressure sensor through this line to the catheter. So this line is always filled with a hyperonized saline to avoid the clotting of the blood and the formation of a clot. This part here is the connector which is attached to the patient monitor, and this is the sensor here. As we said, this sensor is a strain gauge made up of 4, is a Whitson bridge made up of 4 strain gauges. As we can see, it's a very small sensor. This setup which is used in the measurement of the extravascular invasive blood pressure. It's called A-line or arterial line setup. A plastic catheter here is inserted inside in the artery. Then this line will, as we said before, we have this hyperonized saline, which is put in a pressure bag, and we have a pressure gauge to read the pressure. The pressure inside this saline, hyperonized saline, bag should be around 300 millimeter mercury and create a small flow or slow rate or slow flow, which is around 3 millimeter per hour. So the hyperionized saline will pass through this circuit until to reach this point, and the pressure, the blood pressure will transmitted the blood pressure wave directly from blood through this saline, hyperionized saline, directly to the pressure sensor here. And then we said, as before, we have a connector which is connected to the blood pressure, to the patient monitor. Now, an important point we should know about what is a periodic wave. Any periodic wave can be made using a set of superimposed sine waves. So, as we said before, the blood pressure with arterial blood pressure is in a periodic wave, so it can be made using a set of superimposed sine wave. As we can see here, this is a square wave, which is also a periodic wave, which can be made using the summation of superimposed sine waves with different amplitude. Okay, this is a principle in signal processing. So as we can hear, this is the blood pressure, arterial blood pressure wave, which is periodic signal, which can be made using a set of superimposed sine waves with different amplitude. So this means that this wave will be the input through a line. Now we will make a model for this line, which transmitted this wave up to the sensor. Okay, and we will see what will be the impact of this line or this model in the transmission of this wave, which is made up of a summation of sine waves with different amplitude. Also, in the study of the model, we can also use another input to study the impact in the transmission, which is a step response. This is the model which I have talked before. The model which is the catheter with the line which is transmitting the blood pressure wave into the pressure sensor, which is a strain gauge. So here is the input. We put the pressure wave, which is the periodic signal, which is a summation of many superimposed sine wave, and will enter this RLC circuit, which is a second order equation, as we know. And here is the recording of this. As a second order equation, differential equation, we know that we can have a different situation. We can the signal either undistorted or underdamped or overdamped. For example, this is the normal waveform, blood pressure waveform, which can be transmitted in case if we don't have any type of distortion for the pressure waveform. This is a case where we call it overdamped in case, for example, if we have a large bubble, air bubble, or a blood clot inside the line, which is filled with hyperionized saline. For this, we fill it with hyperionized saline to avoid the formation of a blood clot. As a result, we will have a condition which is overdamped. So, till now, we have covered in the extravascular invasive blood pressure. We used the background or the prerequisite of signal processing and the prerequisite of modeling. We used to understand the signal processing was used to understand the periodic nature of the blood pressure waveform, arterial blood pressure waveform, and the modeling is used to understand the impact of the catheter and the line in the transmission of the signal without being distortion of the blood pressure waveform without being distortion. Now we will talk about the third part of design, which is the electronic circuit. This was the conventional electronic design, which was previously used prior to the prior to the use of fast analog to digital converter ADC, fast ADCs like the delta to sigma. As we know, the pressure waveform is an analog in the analog world, whereas the processing will be done in the digital world. If we have a slow ADC signal, we need to make most of the signal processing of in the analog domain, whereas after having a fast ADC, we don't need anymore to make this signal processing in the analog domain. We rather made it in the digital domain. But I will talk about the analog domain to have some idea how was the design of the electronic circuit was done before. So this is the design. As we said, here is a pressure sensor, which is a Whitson bridge made up of 4 strain gauges. Okay, the output of this bridge will be a differential signal. First of all, any type of pressure sensor, we need to make a zeroing for it. Okay, for example, in the case of reading of the blood pressure, prior to start of the reading of blood pressure, you should make the zeroing of this circuit. Okay, so first of all we have to make zeroing, and we also then we start recording. So this is a Whitson bridge which is used to the measurement of the blood pressure waveform. Its output, as we said, is a differential signal. In order to amplify it, what we used here is a differential amplifier with multiple gains. Okay, this is the first stage. The second stage, as we said before, prior to start to measuring and recording the blood pressure, we need to make zeroing. So we make this zeroing using this potentiometer. Also another part, so the second part also is a differential amplifier. So we have a first differential amplifier and we have a second differential amplifier. However, the difference in the first one, we only use this differential amplifier to make amplification, whereas in the second differential amplifier, we have two functions. The first function is a zeroing, and the second function is a calibration of the machine from time to time due to the aging of the different components in this circuit. Okay, this done usually during the preventive maintenance. So this circuit, the whole circuit in this slide, we have the from bridge to here is to make the reading of this pressure signal, blood pressure signal, arterial blood pressure signal. As we said before, we need to calculate 3 parameters: the systolic, diastolic, and the mean. In this circuit, we see this is the waveform which have been measured using the previous circuit. Now we need to calculate 3 parameters: systolic pressure, diastolic, and mean. As for mean, as you remember, in order to measure the mean from this wave, we need to make an integration, and this is the mean amplifier, or what we call it, integrator. Okay, we have 2 buffers, and inside we use an RC circuit. Now we'll move to the third slide, where we'll talk about the systolic detector and diastolic detector, what they are and how they function. So again, we have the waveform here, and we need to have the systolic output. As you see, we have a circuit which is made up of 2 similar parts and with switches. So the circuit is made of a full bridge. Then we have a capacitor, then we have a diode and a resistor. This is exactly similar to the power supply, where we have a sine wave, and we after entering a full bridge, we have a rectified full wave. Then we put a capacitor in order to make smoothing. By doing this, we really is measuring the maximum. By this way, we are measuring the maximum. So imagine we have a sine wave and another sine wave. When we put a capacitor, we make a smoothing for this signal, and then we can have the reading of the maximum or the amplitude, which will be the systolic. So very simple. This, although it appears to be complicated, but it's very simple. We have a bridge and then we have a capacitor, similar to the power supply. You have a full bridge, which make a full rectification of a sine wave. So the negative part will be a positive. So we have two positive, and then we use a capacitor to make smoothing, and then we have the maximum value. By this way, we measure the systolic value. Okay. So why do we need to have two circuits and not one? Imagine we have two heartbeats. In the first heartbeat, what will happen? This capacitor will be charged with the first value of the systolic wave, which is the peak. Then in the second beat, what will happen is the addition of the second beat, the systolic value in the second beat for the first peak. Then we have here is the summation of the systolic wave, where in reality we need to know the systolic value in each beat and not the summation of them. So for this, we use two circuits, as we see here. Okay, one is used for the measurement, where the second will be used to discharge, as we see here, and will be prepared for the second beat. So in the first beat, the measurement will be made here, and this will be used only for discharge. In the second beat, this will be used for measurement, and this will be used for discharging of the capacitor to be prepared to the second reading. Okay, this is happened using these switches, which is controlled by a flip-flop, which is controlled by itself, which has a clock or trigger, which is the heart rate. Okay, so it's a very simple circuit. I will repeat again what is happening here. So we have this wave, which is the arterial blood pressure waveform. I need to measure the peak, which is the maximum, which is the systolic value. This is similar to having a sine wave, and we make as a rectification, and then we use a capacitor. In this way, we measuring the peak of the sine wave. Okay, similar here, we are measuring. However, to avoid the summation, so as we said, we have the first beat and second beat. In the first beat, what will happen if we have only one circuit? We will have the systolic value will be stored in this capacitor. In the second beat, the second systolic value will be added to the first one, and what will be ended is having a summation of these systolic values. To avoid this, we use this circuit with these switches, okay, and controlled by a flip-flop, which have a heart rate clock. Okay, this is the heart rate, which is called heart rate of that patient. Okay, so what will happen in the first beat? This one is used to measure the systolic value, which is stored in the capacitor 1, and in the same beat, the capacitor 2 will discharge its content in the ground. Okay, in the second beat, this will be used for the measuring of the systolic value, which will be stored in this capacitor, whereas this capacitor will empty its charge in the ground through this resistor. The systolic wave, the diastolic wave will be the same circuit as this one. However, before that, we use a diastolic, what we call it, a diastolic inverter, which is just a normal inverting amplifier. So I hope this part is now clarified. So it's very simple. As we said, we have similar to the power supply. We make the rectification, full bridge rectification. We make smoothing by capacitor. By this way, we have the maximum value, which is a systolic. Then we put it through this amplifier, this buffer, and we have, in order to avoid the summation of the systolic and the capacitor, we use two circuits. In one beat, one is used for measurement and the another one will be discharged to be prepared to the second beat. In the second beat, the second circuit will be used for the reading, and the first one will be used to discharge, and so on, using this flip-flop, which is controlled these four switches. The inverting, the diastolic will be the same circuit. However, prior to entering this circuit, we use an inverting amplifier to flip down the signal, and by this way we measure the peak here, which will be the diastolic. So as you can see, here's the signal. The signal will enter here, will be charging the capacitor, passing through the diode, and go through the amplifier. Okay, and whereas in the same beat, what will happen? The capacitor here, the signal will pass through this full bridge, but will not pass because the switch is open and this one is closed. So this capacitor will be discharged through this resistor into a ground. In the second beat, the opposite will happen. Okay, as we said, this was the design used in the prior to have a fast analog to digital converters, whereas currently, due to having a fast analog to digital converter, only we need this part. Okay, so in order to have this waveform, and then the rest of this signal processing will be done in the digital domain and not the analog domain. But I prefer to explain both in order to understand the difference between the old and the new generation of the extravascular invasive blood pressure circuit, electronic circuit. Now the last part in the invasive blood instrumentation will be about the intravascular invasive blood pressure. The difference, as we said before, we don't have an interface as a case of the extravascular, because the sensor is directly inside the blood pressure, so we don't have the fear of a distortion of the blood pressure wave as it transmitted in the line, as in the case of the extravascular blood pressure. So in the intravascular means sensor is the blood pressure inside the blood vessel. And then the signal will be measured directly. It's classified as applied part CF according to IEC, similar to the extravascular one. We can see in this slide two types of the intravascular pressure sensor. Both of them are fiber optic. Okay, both of them are made up of fiber optic. The design is very simple. The catheter head, the head of the catheter is inserted inside the blood vessel, which means here will be inserted inside the blood. This is a thin metal membrane, and we have, which is act like a flexible mirror. We have here's a fiber optics. We have a LED light source and a photodetector. What will happen? The blood pressure waveform will move this thin metal. Okay, the photodiode, the LED light source will provide the light here, which will be having contact with the flexible mirror and will be transmitted to the other part of the fiber optic onto the photo detector. It's very simple and easy. Also, this another type which is used for the measurement of blood pressure intracranial inside for the newborns. Thank you.